So remember, Gauss's law told us that the flux is the electric field times the area times cosine theta, right? And what else was the flux equal to? Flux was also equal to Q inside over a constant. And so if the flux is equal to the electric field times the area, and the flux is equal to Q in over a constant, then this must be true. And we talked about the fact that, remember, flux is this tool that we're using. The next time somebody asks you about flux, with the exception of the next exam, will probably be never, right? But it's this tool that we use because you're definitely going to be asked about electric field. Electric field is something that we're definitely interested in. Flux is a tool that we use to help us find the electric field in certain cases where we have nice symmetry. It's not very many, but in those cases, it works beautifully. So what are those cases? Spherical symmetry. And we did one the other day, but you have some kind of spherical distribution of charge. And that spherical charge is filling the space around it with an electric field, right, in 3 dimensions. So let's draw a Gaussian surface around here. I'll use a blue line. You pick a surface that matches the symmetry of the problem. Because you want, in order for this to be true, the electric field has to be constant over the surface, and the angle theta has to be constant. So we know from spherical symmetry with charge distributions that the electric field is a function of r, right? It drops off as 1 over r squared. So at a given radius, the electric field is going to be constant. So we'll draw a sphere around our spherical charge distribution. You understand the point here. We're trying to find the electric field at some location, maybe right here. I'll put a red. What's the electric field at that location? So we draw a Gaussian surface, an imaginary surface around our charge distribution where the surface happens to fall at our point of interest, right? That's where we're trying to find our electric field. Now we say, we know from Gauss's law that this relationship holds true. So the electric field is constant everywhere over the surface. That's what we're trying to find, right? I'll just leave it as E. The area of a sphere, 4 pi r squared. And what is the angle here? It's the angle between the normal to the surface and the electric field. So my electric field is pointing radially outward, and the normal to the surface points radially outward. So the angle is 0 degrees, cosine 0 degrees. And let's pretend we have a total charge, capital Q, inside there. Gesundheit. And now I can just rearrange these things. I've got a 1 over 4 pi epsilon naught and a q over r squared. And 1 over 4 pi epsilon naught, we get tired of writing that all the time, so we use k for that. That's the constant k we introduced earlier. K q over r squared. So that's the same as an electric field from a point charge. So if we have a spherically symmetric charge distribution, we can just put the whole thing at the center. That's what we did with mass, right? We said the same thing with mass. We had a planet, maybe, capital M, and some other mass out here, little m. And what did we use for the force of gravity between the two of them? What was that r? It was the center. We put all the mass at the center, and we use the distance from the center. We've already done that. Newton had to invent calculus to prove that that was true, but that's, you can, if you take an advanced calculus class, you can do that integral and show that the force out here, due to all the little contributions in a spherically symmetric distribution, sum up the same as if all of it was at the center. Okay, so I just showed you how it works for a spherically symmetric charge distribution. We can also do one that has cylindrical symmetry, like a line charge, an infinite line charge. Let's make it positive charge. So if this line of charge is really, really long, what does the electric field look like? The lines come out. Parallel to each other, right? Remember, we could just sort of, if we have a small line charge that's positive, the electric field lines start to do something like that, right? And if we make that longer, then the electric field lines in the center look more and more parallel. And if we make it infinitely long, then those electric field lines become parallel to each other. We don't have, if it's infinitely long, we don't have any edge effects, right? So what does the electric field look like here? It looks like this. This is our side view. I'm going to draw a top view also. Here's our line of charge, right? And what does the electric field look like? It comes out in all directions. So looking down from the top on that long line of charge, we see the electric field coming out radially all around. And looking from the side at that long line of charge, we see the electric field coming out, parallel electric field lines coming out in each direction. So this is sort of a cylindrical symmetry here, right? That's the shape we would choose for Gauss's law, because we want the electric field on our Gaussian surface. So I guess the question is, what's the electric field out here? Right, at the red X, what's the electric field there due to that charge distribution? So what do? We draw our Gaussian surface with one of our surfaces at that location. So looking down from the top, that's not very good, is it? That's a little bit better. And looking from the side, we would draw a cylinder, right? Something like that. And why did I choose this shape? I'll show you in a second. But what we have to do is sum these up, this EA cosine theta, for every surface of for every part of our Gaussian surface. So what I end up with is EA cosine theta for the top of my cylinder, EA cosine theta for the sides of my cylinder, EA cosine theta for the bottom of my cylinder. And I add them all up, and I have to get Q inside over a constant, epsilon naught. So what's the flux through the top surface? 0, right? What is flux? It's the field lines that are penetrating the surface. And the field lines are parallel to the surface. They never penetrate the top surface. So we get a cosine 90 degrees. We get 0. There's no flux through that surface. And the same is true for the bottom surface, right? Now for the sides, the electric field is constant everywhere. We need the area of the sides, and we have a cosine of 0 degrees. Because the electric field is normal to the surface, and that's the angle we're looking for, right? Between the electric field and the normal, there are 0 degrees between them. So what do we have here? We have E, that's what we're trying to solve for. The area of the sides of a cylinder. What is that? You remember? Here's our cylinder. If we cut it down one side and open it up, we're looking for the height of our times the circumference of the top, right? That gives us the area. So that would be 2 pi r times h. And so I've got my electric field is a constant, Q in over h. And what we typically do, we don't like it to be a function of part of the Gaussian surface. Because what if you draw a different imaginary Gaussian surface than I draw? What if mine is 2 meters long, 2 meters high, I have h equals 2 meters, and yours is only 1 meter high, you have h equals 1 meter. We should get the same answer in the end, right? It shouldn't matter which Gaussian surface we draw. The electric field at that red x should be the electric field at that red x, right? Doesn't matter how we get there. So what changes?